The energy released in these radioactive decays is quantified by the Q value. The general definition of the Q value of a reaction or a decay process is the difference between the initial and final mass energies, where I and F stand for the initial and final particles respectively. In the case of a decay, only one particle is present initially. The decay is possible only if Q is greater than 0, which corresponds to an exothermic process. As an example, the Q value for the beta minus decay reads, where mx and my stand for the masses of the x and y nuclei. Using the conservation of energy in the center of mass frame, we can write where K stands for the kinetic energies of the particles and E star stands for the excitation energy of the daughter nucleus Y. Note that the electron and the neutrino being elementary particle, that is without internal structure, they cannot be excited. If the daughter nucleus is produced in its ground state, that is without excitation energy, we get. The Q value is often important to determine the lifetime of a particle. Often, the larger the Q value, the smaller the lifetime. Note, however, that having a large positive Q value is not enough for the decay to happen, as other factors such as symmetries must be taken into account. The beta minus decay of the neutron illustrates the relationship between Q value and lifetime. The neutron lifetime is of the order of 1000 seconds, which is orders of magnitude longer than typical weak interaction decay lifetime. This is because the Q value for the neutron decay is very small due to the fact that protons and neutrons have very similar masses, which hinders the decay and increases the lifetime. As an exercise, compare the Q value for the neutron decay and for the pi plus decay into an anti-muon plus a muon neutrino, which has a lifetime of 2.6 times 10 minus 8 seconds. As another exercise, show that the kinetic energy of the electron is much larger than the kinetic energy of the daughter nucleus, assuming that the kinetic energy of the neutrino is 0 and that the electron is not relativistic. As a last exercise, calculate the Q value for beta decay of a single proton. Is this decay allowed? We just expressed the Q value as a function of the mass of the nuclei mx and my, which are not exactly the mass of the atoms, the difference being the mass of the electrons and their binding energies. Because some processes, such as electron capture, involve electrons, it is often more useful to write Q values as a function of the mass of the atoms mx, which is the mass of the nucleus plus the mass of the electron, where we have neglected the binding energy of the electrons in the atom. In this case, we have neglected the mass of the neutrino. Beta minus and electron capture decays are similar processes and occur in proton-rich nuclei. Electron capture should be a rare process because it is proportional to the probability that an electron of the atom is inside the nucleus. However, we see that the Q value for electron capture is greater than the Q value for beta plus by twice the mass of the electron c squared. Therefore, some nuclei may decay by electron capture only simply because their Q value is positive for electron capture but negative for beta plus.